Hello everyone, welcome to my YouTube channel. My name is Evidence, and in today's video I am going to show you how to use a Scree plot to explain your PCAs. So in the last video I showed you how to create PCA using a scikit-learn library, and in the next video I will show you how to create a PCA manually. But today's video is going to be focused on explaining your PCA Scree plot using a Scree plot. So in the last video, I also went over a brief overview of what principal component analysis mean. I'm going to skip this for now, but at the end of the video, I'll come back and explain this again if you need to know. But in the meantime, let's go ahead and get started building our Scree plot. So in the last video, I stored our PCs, our principal component, in the variable called PCS. So we are going to be accessing PCS today. So if you see me using PCS, just know that that PCS information is coming from this right here. So if you Google PCA Scree plot, this is what you will get from Wikipedia to tell you that a multivariate statistics, a Scree plot is a line plot of the eigenvalues of factors or principal components in an analysis. The Scree plot is used to determine the number of factors to retain in an exploratory factor analysis or principal component to keep in a principal component analysis. So basically, these Scree plots will help us to determine how many principal components to keep. In the last video, I just used dummy data, but I told you that right here you can put in the value of how many principal components you want to keep. In this situation, we said 2, so we have 2 principal components, and also I told you that your principal component does not embody 100% of the information in the original data set. Your goal is to keep principal components that account for greater than 90% variance in the original data set. So by plotting this Scree plot, you'll be able to find out the percentage contribution of each principal component, to the variance, and then you can kind of pick the number of principal components that account for greater than 90% variance. All right. So with that being said, let's go ahead and get started with coding. So earlier in this notebook, I did import pandas as pd, import numpy as np, import matplotlib.pyplot as plt. So I am going to be using these libraries today. So first, I'm gonna show you something called explain variance ratio. So if I go ahead and do PCA.explain variance ratio, it gives us this value, and if you go back to scikit-learn library here, it tells you that explain variance ratio is the percentage of variance explained by each of the selected components. All right, so that's what explain variance ratio is. We are going to be using that today, and of course PCA is from above here. So PCA is when I instantiated our PCA. Here I did PCA equal to PCA. That's where PCA is coming from. So we are gonna do a number of components is equal to the length of our PCA.explain variance ratio, and then we are gonna do the index is equal to np.arrange, and then we are gonna do number of components, and we can do this right here just to give you an idea of what it looks like. So our number of components is this right, is 2, okay, and np.arrange just gives us index, and we want our index to be the same size as the length of our number of components. And when I finish this, I'm gonna take all of this and put it in a function. make it easier. And then we are gonna do values is equal to PCA dot explained variance ratio. So now we have our index and then we have our values. All right. And our index is basically the same length as our values. That's why we did this right here. So now we are going to define the graph. We're gonna do pl2.figure, and we are gonna set the fixed size is equal to something like the first one is the width. Let's set it to, I don't know, 16 by 6 maybe, or we can just do 18 by 6 or whatever. So you can set the figure size to whatever you want it to be. And then I'm gonna define our subplot, and I'm gonna set so we are basically adding a subplot to our current figure. So we have our figure right here, and now we're adding a plot within our figure. So basically this number right here is telling us the position. If you look at the documentation for subplot, it tells you that you can do position. Position is the same thing as number of rows, number of columns, and number of index. So basically this is the position for the plot within your plot. All right, and it tells you right here that position is a three-digit integer, where the first digit is the number of rows, the second is the number of columns, and the third is the index of the subplot. And then and all integers have to be less than 10 for this to form to work. So basically right here I'm saying I want number of rows to be 1, I want number of columns to be 1, and I want the index to be 1. And index starts at 1 right here in the upper left corner and increases to the right. So I'm just adding a subplot here, and then I'm getting the cumulative sum of our values. So I'm gonna call it cum values, or cumulative is equal to mp.cumsum, and we are gonna put in values here. And now we are going to create a bar graph. So this subplot right here, we are going to create a bar graph using this subplot. So we're gonna do ax dot bar, and we want a bar graph between our index and our values. The index and values we just defined. And then we want to plot our index and our cumulative sum. Okay, so right here, right, we first define a figure, then we create a subplot within our figure, and then we get the cumulative sum of the elements of these values, which is our PCA explained variance ratio. And then we create a bar graph using the index and the PCA explained variance ratio. And then we create a plot using the index and the cumulative sum from the explained variance ratio. Let me go ahead and run this first. Well, I don't want any results yet, but I ran that so that I'll be able to extract stuff from these values. We can go ahead and do something like values at position 0, for example, times 100. Tells you it's 100%, okay? Or we can use something like 1, and it tells you this. Now if we turn this into a string right here, this is what it looks like. And if we just want this right here, we'll do something like this. There it will just give us the first 3 letters in the string. So I'm going to be using this syntax right here to annotate our graph. And when I use this syntax to annotate our graph, I don't want you to like get confused, like what is she doing? Okay, so basically, I'm taking the values, I'm multiplying it by 100, I'm turning it into a string, and I'm just extracting the first three um, characters in the string. And that's how we are going to annotate our graph. And I'm going to do this for every single value in our explain variance ratio. So we want to do this 2 times since our number of components in this situation is 2 because the length of our PCA explain variance ratio is 2. We want to do this only 2 times. And if the length of our PCA variance explain variance ratio is 5, then this will happen 5 times. So we want AX at annotator or dot annotate, and then we want to put everything in percentage sign. Basically, this is what I just showed you. Values at position I times 100, and then we want to get the first 3 index. And if you look at the documentation for annotate here, it tells you that we have to provide a tuple of x coordinate and y coordinate, specifying where you want your annotations to go. So this is the annotation for the s coordinate, and now this is the annotation for the y coordinate. So basically here I'm saying the index at position I want it to have the values located at the same corresponding position. Val in this situation, I do for I in range so often that I forget that I'm using a different variable. And then we can add a few other parameters like vertical alignment. We want our vertical alignment to be bottom, and then we want our horizontal alignment to be center. And then we can set the font size to something like I don't know, 6. You can play around with this and manipulate your graph a little bit. But this is how we are going to be annotating our graph. And now we are going to make our graph look a little bit prettier. So we're gonna say x.axis. We're gonna set the thick parameters. I don't know if you know what thick parameters are, but they are like those tiny lines. And we want to set our thick parameters, and we want the width to be equal to 1 maybe. We can come back and change this. If our graph doesn't look right, we'll come back and change it. We want the width to be, let's say, 3, and then the length to be equal to 12, or I don't know, 15 or something. It doesn't matter. I mean, it does matter, of course, it will affect how your graph looks, but these are things we can change. Just so you know, so this is like defining the values to be graphed, defining our graph parameters, and then this is annotating our graph, and this is like setting other parameters for our graph, and this is labeling our data, and then ax dot set y label, and then we want plt dot title. We want to add a title. So with all of this set, let's go ahead and run this. Oops, we got an error message. Let's see. So many typos today. So this is x-axis, and yeah, there we go. Wow. So this doesn't look very good because of I did this using a dummy data set. It doesn't look very good, but that's okay. I'm gonna show you a Scree plot that looks really good. I'll go ahead and copy this and put it in a function. So I'm just gonna call this Scree plot function. And I could have done this from the get-go, but I wanted to take some time to explain to you, the code within the function. So let's just call it def Scree plot. So we've created a function for our Scree plot, and now we can use it over and over again whenever we want to. So I am going to grab different sets of data, and I'm gonna do PCA on it real quick, and then I'm gonna do this Scree plot again, and I'm gonna show you a Scree plot that looks nice and kind of really helps with explaining stuff. So I went ahead and created a new PCA data frame, and I'm going to be using that new PCA data frame here to do our Scree plot. And I went ahead and took our Scree code and put it in a graph, so I can just call this again whenever I need to. So I'll go ahead and run this, and then I'm gonna do Scree plot, and in parentheses I'll do not PC because that is the graph. Actually, I called it not PCA. And as you can see right here, it kind of shows us only 2, and that's because we chose 2 as our principal component. So if I go back up here to this and change my PCA to, like, let's say 10, all right, and let's go and run this, and I don't need to run this again. But if we go back down here to our graph and let's say run this again, now we have a nicer looking graph. Okay, so the number of bar graphs you get here corresponds to the number of principal components that you picked. In this situation, the first time I picked only 2 principal components, and the second time I picked 10 principal components, and that is why we have 10 bar graphs here. And basically this is what a Scree plot looks like. And here it tells you principal component 0, and it tells you you really can't see these numbers very well, so let me see if I can make it bigger. Alright, so now you can see the numbers a lot bigger, right? It's telling you that the first principal component explains about 34% of the variance, second principal component 14% of the variance, third principal component explains about 10% of the variance, so forth and so on. So how do you know how many principal components to choose? Well, the number of principal components that you choose depends on you want to choose enough principal components to account for greater than 90% of the variance in the original data set. So that is basically it for this video. That is how you would create a Scree plot. And just to recap real quick, I showed you how to create a Scree plot line by line, and then we kind of did a Scree plot with a dummy data, and then I put the Scree plot in a function, and then we got a different data set so we can better visualize a Scree plot. And this is what it looks like. I hope you like this video. If you like it, please give it a thumbs up and subscribe to the channel. If you made it this far in this video but you didn't like it, please give it a double thumbs down and still subscribe to the channel. And like I said earlier, I wanted to kind of explain to you what PCA means a little bit. I did this in the last video. So basically, PCA is a dimensionality reduction technique, and it transforms a high dimensional data set into a new lower dimensional data set while preserving the maximum amount of information from the original data. And whenever we are dealing with PCA, we encounter eigenvector and eigenvalues. And basically, eigenvector and eigenvalues is eigenvector is a vector on a graph that doesn't change direction but can be scaled up or scaled down. And the value that scales it up or down is called the eigenvalue. And here, like I've been saying, principal components does not represent 100% of your data. The goal is to choose enough principal components to represent greater than 90% of the variance in your original data. And the pros of PCA is that it reduces dimensionality, and the con is that we don't know which features combine to create your principal component. And so we are trading off predictive power / ability, And we're also trading off explainability of our data in order to reduce dimensions. You can get this notebook that I use in today's video by going to machinelearningeducation.com. This is a platform I created just for you. And once you are here, you can click on free data science resources and you'll be able to get access to this page. And right here on this page, you can get access to my data science tutorial Python notebooks. So I create a lot of YouTube videos and a lot of blog posts, and I just find it easier to take all those notebooks and put it under one platform, and that's machinelearningeducation.com/free. You can also find me online at evidencen.com. This is my primary website where I have my data science blogs, and as time goes by, I'll create more and more data science blogs. And once you are here at evidencen.com, you can also click on this to get access to the notebook used in today's video. That's it for this video. Thank you for watching, and I'll talk to you on the next one. Bye.